Welcome to the weekly MCube seminar, and today we're very pleased to have George Bryan as our speaker. George got his PhD in meteorology from Penn State back in 2002. He was an NCAR postdoc from following 2 years. He's presently a senior scientist at MCube and a section head of dynamical and physical meteorology. George is the recipient of the Clarence Leroy Meisinger Award in 2011 and the Banner I. Miller Award in 2010. In 2019, George received the UCAR Outstanding Achievement Award for developing and supporting the well-known and widely used CM1 model. George is well known for his studies of moist convection, including a wide range of applications from elementary cumulus convection to mesoscale convective systems to tropical cyclones and probably beyond. He has also participated in a number of field programs, Vortex 1, Vortex 2, BAMX, and most recently he's been collaborating with the folks dropping drones into tropical cyclones. So today the topic of the talk is the turbulent kinetic energy budget and a large-eddy simulation of a tropical cyclone.
Thank you, Rich. All right, hello to everyone online too. I know quite a few people told me they were going to join us remotely. And this is some work I've been working on quite feverishly lately. In fact, for those of you who wonder why I'm not responding to your emails, well, this is why I've been working on this, especially when I agreed to give a seminar. It's like, no, now I got to have results. Part of the reason I mention that is some of these slides and results are pretty new. My co-authors haven't seen it yet, so blame me if they're wrong, not my co-authors, which include Rich, and also Chiboise and David from University of Notre Dame. Both of them were visitors here recently. David was, of course, a postdoc here. Thanks to my sponsors, NSF, NOAA, ONR, and Sizzle Supercomputing, which played a big role in some of this work. Okay, here's some overall outline for my slide. First, I'm going to answer this question, what is TKE, for those of you who don't know. Some of you who work here may be wondering what, better question might be, what is TKE-B? So if you look at the staff notes from today, it's TKE-B budget. And that's just a typo, no big deal. Although I was talking to Neely this morning, and I said, you know what, I should take advantage of this and come up with a new acronym, so I did. So TKE-B stands for TKE, baby. I was supposed to use my best Austin Powers voice, but I'll just say groovy and leave it at that. Now, what is TKE and why is it important? Why do we care about it? That'll be the first thing. Sorry. Kind of an expanded section on computing TKE budgets and numerical models. I'll explain why I kind of added that recently. I hope that doesn't take up too much time. And then I'm going to get to the main feature, which is the TKE budget in a high-resolution simulated hurricane. Okay, what is TKE? I decided to start by following lazy meteorologists everywhere and just go into the AMS glossary and pasting in the text. And it's actually quite insightful. So the TKE stands for Turbulence Kinetic Energy, is the kinetic energy associated with eddies in a turbulent flow. Now, if you're not familiar with these terms, eddies and turbulent flow, I'll get to that in a moment. But I think that pretty much summarizes how most people sort of mentally or conceptually understand what TKE is. And I like this quote from Stoll's Boundary Layer Meteorology textbook too. He said, turbulence kinetic energy is one of the most important variables in micrometeorology because it is a measure of the intensity of turbulence. And I think that kind of well summarizes as well what TKE is, and I just like the fact that he used the word important. It really is one of the most common metrics of turbulence that you'll see in the literature in the community. Okay, as I said, I was going to follow up on what these terms eddies are and what turbulent flow is, and everyone likes to use the joke that turbulence is difficult to define, but you know it when you see it. And here's two pictures which are, I think, clearly turbulent flow. On the left, image of a gravity current. This is just dense air that's spreading along a lower surface. They often form these sharp fronts at the leading edge, and they have turbulence that forms along the interface between the fast-moving current below and the slower or even non-moving environmental layer above. And this is a nice conceptual figure here showing the flow associated with the gravity current has a lot of kinetic energy, but that's not the kinetic energy we're talking about. We're talking about the kinetic energy associated with these bumps and swirls. And if you watch animations, you often see kind of a sense of rotation in turbulent flows. And that's because vorticity is a very important quantity in turbulent flows. It's associated with, particularly the stretching of vorticity is associated with collapsing of energy to smaller scales. And this is an important property of turbulent flows where you have many scales of motion. On the right here is a cumulonimbus cloud. I've used this image quite a lot. It's part of the NCAR stock images online. So again, we're not talking about the flow associated with the cloud itself, which has a pretty strong updraft with a lot of kinetic energy. We're talking about this kind of smaller scale features like this big round, I don't know what to call them, turrets or bubbles. What do you call them these days, Hugh? Starting bubbles and things like that, I think. Yeah, but we're talking about these kind of smaller scale rotational features. And TKE is just a way of quantifying the amplitude or magnitude of those structures. And it has implications, which I'll explain in a moment. And I wanted to show this image here. As Rich said, I've been involved in a very small way with deploying uncrewed aircraft systems in tropical cyclones. These are kind of small. You can see a picture of Joe Sion in the bottom left here. We wrote a paper which is published in BAMS. This is you get a sense of how big these drones are. They're relatively small. They're deployed from larger aircraft, which ferry out into the storm and release the drones from within the storm. And they fly around and collect all kinds of cool data. This is a nice photoshopped image that they had here in the cover of BAMS, which no one saw that image, I don't think, or that issue because it came out in April of 2020, and it was all sitting in people's mailboxes in their office for 2 years. And then when they came back in, they had a big stack of them, and I don't think anyone ever saw it. Oh well. There's this nice figure in that edition of BAMS, a figure I helped make. I think Ron Dobesy made the time series, and I added on the bottom here estimates of TKE for 2 different segments. And so what's notable here, these are the 3 components of velocity as measured by one of these aircraft. And I believe it was Hurricane Michael in 2017. Right around it was a Category 4 storm at the time, I believe. And so again, what we're talking about are these fluctuations, or the kind of the smaller scale structures within the overall system. So we're not talking about the kinetic energy associated with the tropical cyclone. We're talking about the kinetic energy associated with these fluctuations. And notice how they get much larger as you get farther along this time series, and in fact, closer into the center of the storm as it happens. Some quick math here in the bottom for people that are interested. You calculate these fluctuations by subtracting off usually a mean value, or sometimes people take time series like this and they'll fit a polynomial. There's various ways to do this, but then the TKE, often called lowercase k in a lot of disciplines. In meteorology, you'll see the letter E used instead. It's 1/2 times basically the 3 variances of the 3 components of wind speed summed together. So that's what TKE is in a technical sense. Switching gears a little bit, I want to show this figure here. TKE is very poorly understood in hurricanes, which is part of the reasons I'm doing this study. But a lot of properties of turbulence and TKE are comparatively better known and better studied in other disciplines. So I like this paper from Mung and Sullivan, 94, just a few years ago, right, Peter? Yesterday, okay. So they did this nice study. I think I was forced to read it during one of my classes in grad school. It's a simulation with a Large-Eddy simulation model of a shear-driven boundary layer or planetary boundary layer on the left and a convective boundary layer on the right. And convective means it's, in this case, heated from below. It's like a sunny, warm day in which the sun's warming the ground, and then you generate turbulence. And on the left, this might be like, I don't know, think of a case with strong wind speeds, like the nocturnal low-level jet, for example. This shows the 3 components of TKE, so you add these 3 together, and you get twice the TKE. So one thing to know is that convective boundary layer it tends to have more uniform TKE with height, I would say. Not always, but certainly in this case, if you added these 3 together, it would probably be about uniform. And shear boundary layers are different. They have TKE, which typically maximizes very close to the surface, and then will often decrease with height. And that has to do with because the shear is quite strong at the surface. So the question, or one of the questions I'm hoping to answer as part of this work is, are hurricane boundary layers more like convective boundary layers or shear-driven boundary layers? And how does that help us in our things like PBL parameterizations for weather prediction models, for example? And as I said, the title of this talk and the ultimate topic of this talk is the terms in the TKE budget. So what is the budget in terms of the tendency terms that govern TKE? What makes it large in certain places and small in others, and how does it evolve in time? And so they had this nice TKE budget in this paper. And by the way, Z over Zi, that's the non-dimensional height, non-dimensionalized by the boundary layer height. So this is 1 means the top of the boundary layer. In the shear case, as you see in a lot of shear-driven boundary layers, it's just the what's called the shear production term balanced by the dissipation. Those terms are by far the most important. Other things like turbulent transport, pressure can be, and a buoyancy term up maybe at the top of the boundary layer can be important, but shear-driven boundary layers tend to be dominated by these terms. And then convective boundary layer, much more complex. The buoyancy term, of course, plays a big role. Turbulent transport also plays a big role. I think this is, this dash term here, the turbulent transport of TKE is just like, the transporting of TKE by these eddies up and down. I think that's one of the reasons these tend to be more mixed. But also, stable or unstable stratification allows eddies to kind of go freely up and down the boundary layer, if you will. So this is kind of motivation. I don't know if anyone's done a proper TKE budget in a hurricane before, at least not for like an entire hurricane like we're trying to do. And then tying it back into other models, this is a couple figures from a study I did with my colleague Xiaomin Chen from a few years ago. Hello, Xiaomin, if you're listening in or watching the recording. We were looking at TKE as predicted by a boundary layer parameterization. And specifically in the MYNN code, which is in WRF and MPAS, for example. I know here on the left, several of the turbulence codes in WRF have TKE governing equations that predict the evolution of TKE, including the MYJ. Club in the climate model doesn't have a TKE equation per se. It actually predicts the 3 variances, the U squared, V squared, and W prime squared, and so from the sum of those you can get the TKE. But this is what the MYNN scheme produces in a hurricane simulation. So this is plotted in terms of radius with the eye of the storm here in the left-hand side of these panels. I think the red contour, if I remember correctly, is the outline of the eyewall. So this is where the heaviest rains are, and as I'll show a little bit later is where the strongest winds are. So you can see from this case, the TKE is like I showed before for the shear-driven boundary layer. It's kind of a maximum near the surface and decreases as you go upward. That's in the inflowing boundary layer down near the surface. In the eyewall, things are a lot more complicated. And as I'll show later, there's some terms that should probably be added to this equation that aren't there now. So this is the equation that's used in MYNN. They actually integrate an equation for Q squared. It's a pretty common variable in micrometeorology. It's defined as twice the TKE. You can see there's terms for mean flow advection, turbulent transport. There's your dissipation term, which has to be parameterized. There's some uncertainty associated with this. And there's terms I showed before. That's what they look like mathematically. I showed them in the previous slides, the shear production term and buoyancy term. And so this is why it matters. MYNN and similar types of codes will use this prediction of, in this case, Q squared, and take the square root and use it to define an eddy viscosity, which is then used to actually accomplish vertical transport, the mixing of moisture away from the surface over the ocean, for example. And here's what the eddy viscosity field looks like, or eddy diffusivity, depending on your preference. And again, it's very high in the eye, the eye wall of the hurricane, but should it look like that? We don't really quite know. So one of the things we hope to do with this study is do a Large-Eddy simulation where you're not parameterizing the TKE, and you can retrieve the budget and you can look at cases like this. So that's the motivation for this work. Unless there are any questions, I'm going to move ahead to topic 2, which is how you compute not only TKE budgets, but budgets of kinetic energy and other high-order variables in numerical model output. And to motivate this section of the talk, I wanted to revisit Dale Duran's talk from a couple months ago. Dale was visiting, he was giving some talks on machine learning, And he had this slide, which he was showing in the M-Cubed Happy Hour seminar series. And so he said he wanted to acknowledge, traditional numerical weather prediction models have their advantages. They have equations that allow for budget studies, and he talks about how mass budgets are easy to close. And he shows this figure, which I think shows that the precipitation over an area is proportional to the net water vapor convergence, and that makes a lot of sense. But he had this sentence here, which if you were watching a talk, you may have seen. I'll read it for you. Budgets for quadratic quantities, such as kinetic energy, KE, only close if you are George Bryan. And I believe he didn't actually explain what this meant. And so some of you are probably wondering, what the heck is that about? And I was actually sitting at home, working from home that day, watching remotely, which is how I was able to get a screen capture. And I was literally laughing out loud because I know Dale met with me a day or two before his talk, and he's like, "Oh, George, what you working on?" And so I was showing him some of this work, and he's like, "Oh, I'm calculating the budget of the kinetic energy." And he quickly said, does the budget close? Does it add up? Does it reconcile? In other words, mathematically, can you account for everything? And I said, yes, but it took me a while. And we talked about that for a while, and he went up to the chalkboard and just, had some ideas. I told him what my main insight was, and he's like, oh, that's kind of interesting. So I think he was planning on saying in his talk here that kinetic energy budgets rarely close, or no one can get it to close, or it's really hard, or something like that. And then he for some reason, changed it into focus on me. So that got me to thinking, maybe I should actually present this somewhere. And I thought about giving in a happy hour, but I don't know, here we are, it's an M-Cubed seminar. Give this talk, and I have this section on focusing on particularly kinetic energy and budgets. And so what I want you to know before we leave here today is that you too can close your energy budget. Or I was playing around with this, trying to have some fun. It's like, I want you to have a balanced budget. It's not just a George Bryan thing. Okay, so what is this about kinetic energy? We're gonna set aside turbulent kinetic energy for a moment, which is just like the energy associated with the perturbations in the flow. And let's look at the total kinetic energy. And I'd say most atmospheric models, the most commonly used ones, don't have equations for kinetic energy. They have equations for velocity components or something similar. So UVW, and so you can't go into the model and say you just pull out the terms to the kinetic energy budget. You have to pull out the terms for the UV and W, the three velocity components, and then retrieve what the kinetic energy budget must be. Okay, so here's a velocity budget in tensor notation. So there's three components to the velocity here. And then I'm just gonna, for the purpose of this talk, I'm just gonna write the so-called forcing terms on the right-hand side of the equation as just advection, pressure gradient, buoyancy, the tendency caused by subgrid scale turbulence, which is parameterization and so forth. And so to form a kinetic energy equation, it's simple. You just multiply by UI, or if you're in vector form, you would dot the velocity vector times your equation. And so the left-hand side can be rearranged, use the chain rule, pull that UI inside. This is where the 2 comes from, when you pull that UI inside here. And then we're just gonna keep the tendency terms on the right-hand side in this simple form here. So this is like, take the pressure term for example. It's U times the pressure gradient in the X direction, plus V times the pressure gradient in the Y direction, plus W times the pressure gradient in the vertical direction, and so forth. So those of you who are turbulence people will know that these right-hand side terms are often rearranged further to provide physical insight. Like earlier, I was talking about shear production term and turbulent transport. Let's not do that now. Let's just keep this advection term in kind of one bulk term. And the argument here being is if you can't get this to reconcile and to add up, to have the left-hand side equal the right-hand side when you do these calculations from your model output, then if you can't do it in this simple form, then why bother going to kind of more complex formulations of this equation? So to this end, this paper came out a few years ago, Heinz et al., 2015. I noticed this. This is a study about budgets of high order variables like fluxes and TKE an equation. And I'm going to kind of pick on them here a little bit, but this is pretty common. This is, I'd say, if people plotted their data like this, you'd probably see this a lot, where this is a lot like the one I showed earlier from Mung and Sullivan's paper. There's kind of 4 main terms. The buoyancy term in red, turbulent transport term, there's no shear in this case, so there's no shear production term, and all the advection terms are basically associated with turbulent transport on the average across the domain. Here's your pressure gradient term. It kind of changes sign from the top to bottom of the boundary layer. The black is your dissipation term. Okay, most studies you'd see just those 4 terms, but these authors did something I was glad I can see. They added all the terms together, and this orangish line is the residual, and that's the sum of all these terms. And now this is important that this is not 0, because it should be 0 in this flow, because it's a statistically steady flow. In other words, things aren't really changing much after a certain period of time in the simulation. In every snapshot you look like, it's turbulent flow, it looks different, but it should have the same statistics. And you can show that calculating the left-hand side of this equation here, that's 0, and then you calculate all these terms on the right-hand side, you should add them up. They should be 0 for this case, but it doesn't add up. So I was exploring this further for some other reasons, and Ned joined me in a study that we presented at the AMS annual meeting in the Turbulence conference. And I basically reproduced this study more or less. It has CM1 simulation, convective boundary layer, 20-meter grid spacing, heated from below, wildly turbulent, and here's my budgets. And it's almost exactly the same as theirs. You can see I've color-coded it again. And the residual, which is the sum of these 2 terms, is, again, it's too big. In fact, it's almost exactly the same as theirs. They came up with a non-dimensional value of 0.2, 0.25, and I have about the same. But I made an assumption here. I said, okay, most people are probably going to calculate these budgets by just taking their model output, your WRF out files, for example, and calculating these terms, and they're probably just going to do this simplest thing in many cases, like for your advection terms, it probably would be common just do second-order centered finite differences for the gradients. The UdUdx, for example, is one term you need to calculate. Just do that centered order. It's easy, probably accurate. And one of the points of this study, and there was multiple angles to this that Ned and I were looking at, but I said, okay, what would happen if I did second order? But I know I'm running 5th-order advection calculations in CM1, both horizontal and vertical. So what happens if I calculate my advection terms using model output, using 2nd versus 5th order? So you do 5th order, and boom, this orange line is now, you might not be able to see this dashed gray line, but that's the 0 line, and it lines up, very nicely. And you can see all I did here is I just changed the calculation of the advection terms. So kind of the point of this study here was use consistent numerics. That kind of makes sense, actually. If your model thinks this is what UdUdx is, then you should calculate UdUdx that way. Pretty simple. So Uncle Sam said, I want you to party. You got your budget to add up. I like to have fun during my talks. But it turns out there's more. If you look real closely, there's a residual up near the entrainment layer near the top. It's not quite 0. Probably small enough for most applications, but kind of maybe something we can fix. But there's more too when you go to other cases which might have more extreme conditions. So I came up with this technique a few years back in which you can kind of simulate a small patch of the hurricane boundary layer in kind of a similar way as these studies I've been showing you before, the Hines et al. Study, this convective boundary layer case I just showed. And so this method, kind of conceptually, imagine you had a tropical cyclone, and these oranges and reds are the wind speed. I want to simulate the boundary layer like out here at some distance r from the center of the tropical cyclone over a kind of a 5 kilometer by 5 kilometer-ish size domain. So the details are in this paper published in 2017. Here's some figures from that paper, some snapshots of the wind speed down low near the surface and kind of maybe a quarter of the way up the boundary layer. Clearly turbulent flow. And like a lot of shear-driven boundary layers, the hurricane boundary layer has these kind of notable streaks and linear-like structures in it. I did some calculations of mean wind speed compared to the observations. I'm not going to go into the details. The right here, vertical profiles of momentum flux, vertical momentum flux. You can see how the model overestimated momentum flux by quite a bit. But I think we solved that problem in the follow-on study with Xiaomin, which we published a few years ago, which we paid a bit more careful attention to the buoyancy, which prevents the boundary layer from growing too fast. And so I'm actually following the technique in Chen et al. 2021 for this study. And so I basically ran a case like that. So this is, I think it's category 3 magnitude winds. It's like 70 meters per second at the top of the boundary layer, like 50 meters per second at the bottom of the boundary layer. Quite strong winds. And here's what it looks like if I do that same technique again. Let's just take model output process it through some, informed but maybe simple calculations, and so do second order center finite difference again, and you end up with this residual term that's gigantic, or where I come from, we call that huge. It's a technical term. Way too big. So this is, I don't know what you thought about the budgets in previous slides, if that was reasonable work with. This is clearly not. It's just totally unacceptable. And there's nothing fancy here. All I did was change the environment. I just went to stronger wind speeds. Significance of that is strong wind speeds, I'm running with a Courant number close to 1, and so features in the model are kind of moving across the grid quite quickly. And so the assumptions you make in your numerics are a lot more important than in kind of weaker flows where structures sit on the grid and kind of evolve more slowly, perhaps. So I think that's the physical insight between the big difference here. So what happens if I go to fifth order finite differences? It's just not much of a change. I definitely reduced the error, but there's still this huge error. And what's going on there? In fact, Uncle Sam was like, "Oh, George, I thought you said you figured this out." But anyway, this is what I was talking to Dale Duran about. This is the conceptual insight. And so one slide here of some numerical methods and a little bit of simple arithmetic. I was talking about this with Dale, but I think I'm going to follow this study by Gassmann and Herzog. Some of you might know Alma Gassmann. She visited here about 10 years ago, I think, helped with the numerics in the MPAS model. So I'm going to follow their notation. So say you're marching forward in time. In a model, you don't have continuous variables. You have discrete variables in time and space. And so you're marching forward from different time steps. And we're going to look at the jump forward from n to n+1 over delta t. So you have two variables in your model, A and B, just a generic variable. It's reasonable to discretize them this way, A of n+1 minus A at n over delta t, and B at n+1 minus B of n over delta t. And one thing I love about the Runge-Kutta integration technique I use in CM1, which is also in WRF, is this is exactly how it's done in the model. If you're using like a leapfrog model, you might have to do a little bit more complicated arithmetic. Then they say, okay, assume you have this variable too, called A times B. Okay, it's reasonable to discretize it as A n+1, B n+1, minus A n B n over delta t. So Gassmann and Herzog pointed out there's just some consequences of doing that. You can rearrange these terms. I'm going to blow through the details here. If you add and subtract the same term here, you can do a different term here, basically A n+1 times B n, or A n times B n+1. You end up with these relations here. You get the B tendency, which is something we're interested in. We can get that easily from the model, and the A tendency. But one of these tendencies is multiplied by B at time n, and the other should be multiplied by A at time n+1. Or conversely, A at n and B of n+1. So the time levels you choose for some of these budget calculations are not arbitrary. So if you have model output, which you just dumped at one time, you don't have these different A's at two different time steps. You usually just dump it all out at n. You don't have n-1 to help you with some of these calculations. So I had been assuming in some of my diagnostic before, just kind of the simplest thing, a reasonable thing. I just use A of n and B of n times these tendency terms, which are, I was calculating actually the pressure gradient term, for example, multiplying that by A and B, or actually U. I'll get to the U equation in a moment. But anyway, this is kind of interesting. And this is maybe this has probably been known for decades, but I kind of picked up on this from Gassmann's paper a few years ago. And if you take the actual equation and subtract it from the estimated equation, you can find you're basically incurring an error, which is proportional to the tendency of the two variables. Yeah, and there's a lot of details here, but let me jump forward to the kinetic energy equation. Now let's say our two variables, A and B, are actually U. So we want to form a U squared equation. And you can follow through the math here. But here's the correct discretization for calculating kinetic energy terms. It's the time tendency of U squared over 2 is the tendency of U over a time step times U averaged over that time step, or U averaged at the beginning and end of the time step. This is just math. In fact, yeah, there's Uncle Sam again. Do the math. So that's how you can get your budgets to reconcile. Some of these details, if I'd gone to, I don't know, Bill Skamrock's office, he probably would have told me to do this years ago, but I never really considered some details like this. So let's step through this hurricane boundary layer case again. Our huge budget when we use second order finite differences and just standard model output. There you go, fifth order advection and standard model output. And there's if I actually correctly do that temporal discretization, such as I described before. So what I did here is I actually went into the model and I said, okay, I did two things. I actually grabbed all the tendency terms from the model itself, like the advection calculation, the pressure gradient averaged over the small time steps and the split explicit technique, dumped all those variables out, and I wrote out basically this term, u at n, and it's actually, I take it from the previous time step, so it's actually u at n minus 1 plus un over 2. So I have that, and then I can do all my math. And when I do that, perfect budget. Residual small, including at the top of the boundary layer. Uncle Sam tells me I can party again, so yeah. Okay, so that's my overall lecture on how to do budgets and model output. I'm gonna jump ahead to hurricanes, which is the point of this talk, but one more point I wanted to make here. Experts in this field know that these auto-ordered advection schemes that are available in like CM1 and WRF and other models are actually, can be written in terms of two terms. So the fifth order advection is the sixth order advection plus basically a high order diffusive term, which I'm going to show in purple in the next couple slides. And in the light blue here is sort of an even ordered non-dissipative term. So what I was doing before is just the sum of these two terms. That's the total advective tendencies. What happens if you do these TKE budgets with these two terms kind of teased out of each other? Here's that same budget. The advection term actually went up. So the sum of this purple and the light blue is the same. It's just now I split it up into what's a very large positive term and a negative term. And I was actually a little bit surprised by this. The dissipation you're getting from this numerical scheme, especially this, again, you're running this model, this pretty high Courant number. It's higher than you might think. It's about, I think, 40% of the total. So if you add the black, which is what you're getting from your parameterized turbulent scheme, your Smagorinsky or your Deardorff type scheme, if you add these two together, then the purple is about 40% of the total. More on this later. One of the reasons I wanted to step through this detail is I've been doing my hurricane simulations actually teasing that part out, and it's going to be in some of my slides later, and I wanted to cover it in this section to see what the implications were. Maybe I'm going to have a happy hour talk later. I've been actually playing around with this, saying, well, what happens if I went to even higher order numerics? Or what happens if, like in WRF, I chose third order as my default vertical advection and stuff like that? It's actually kind of interesting to see what comes out in budgets like this, particularly for this kind of hurricane case. Okay, finally, we're getting to the topic of the seminar, the primary talk, the main event, as I called it, TKE budget in a simulated hurricane. Thought I'd show this image. Chris Davis, I think, showed the same exact image at his seminar last week. It's polar orbiting infrared satellite image of Hurricane Irma as it was crossing over the island of Barbuda, which you can see, hopefully you can see here the white contours of the island of Barbuda, which is about 10 kilometers wide. Yeah, this is a category 4 or 5 when it made landfall. It was kind of historic. The island, all the infrastructure in the island was basically destroyed. Everyone had to leave. There was no infrastructure anymore. There was no water, there was no electricity. And so for the first time in like 400 years, the island was uninhabited. For about a year, they eventually fixed things and everyone came back, but it was quite notable. This is the island of Antigua down here, St. Martin over here. But what I wanted to show here is notice how turbulent the flow is. And I like looking at these features here. I don't even know what these are. I don't think we have names for some of these streaks and features, but I think they're related to what I'm going to be studying later. A few details if you're not familiar with hurricanes. The eye, of course, is this cloud-free region in the center where winds are relatively calm. The eye wall is the area that surrounds the eye where you typically have the deepest convection, in this case, the coldest cloud tops, as you can see in the infrared image. Notice there's all kinds of structures up in the outflow too, associated with probably gravity waves. There's just all kinds of physics and dynamics going on in hurricanes. A lot of fun to study. I like to show this image from one of Kerry Emanuel's books. It's sort of called The Anatomy of a Tropical Cyclone. I already told you about the eye. and the eyewall, which is the region that surrounds it. But if you do a vertical cross-section through that and look at the details, the wind speeds are highest in the eyewall and typically very close to the surface, about 500 meters on average above the surface, where you see the strongest winds in hurricanes. Rain bands are the areas kind of far away from the storm, which have some deep convection too, but not quite as deep typically, with not quite as high winds as the eyewall. You can see the type of the scales here. The inner core of a hurricane is a couple hundred kilometers wide. It's huge, and it takes a lot of computing power to simulate this stuff with high resolution. And all my simulations are going to look like this. They're going to be over calm ocean waters. Well, not calm, but constant ocean waters. We don't have any land. It's not an actual case. It's an idealized case. And one last figure, and I think this image Chris showed last week too. We didn't collaborate. It just sort of happened as I was preparing my talk. We had the same figures. This is a composite analysis using Doppler radar from the NOAA flights that fly into hurricanes all the time for reconnaissance regions. This is a study done by Rob Rogers and his colleagues. Rob will be visiting here in a couple weeks, actually, if you want to grill him on some of his work. And so what I'm showing here on the left-hand side is the tangential velocity. That's the cylindrical coordinate system. That's the magnitude of velocity going around in circles around the center of the storm. And that's plotted in an RZ coordinate system. Z is the height above the ocean surface, and R is in this case normalized by the radius of maximum winds. So a value of 1 is right where the maximum winds are. And you can see that the winds in hurricanes actually kind of slant outward a little bit from they're closest to the center of the storm down near the surface, and they tilt outward. What I really wanted to show, though, is this figure on the right. This is one of the few analyses of turbulent kinetic energy in hurricanes that you'll see. It's actually not quite analogous to what I'm doing. I think they did an analysis of the spectrum width of the radar, the Doppler radar radial velocities, and so it's not quite the same. You don't calculate an average, and it's a little bit different. So the magnitudes are actually kind of a lot lower. They get maximum TKE of about 13 meters squared per second squared, and it's actually a composite. They're doing TKE averaged over a bunch of storms, and that's why they do this non-dimensionalization of the radius by the radius of maximum winds. But what I do want you to take away from this figure is the pattern of the TKE. In particular, the highest TKE is in the lowest 2 kilometers or near the surface. That's not surprising. What probably is surprising is the maximum TKE is not where the maximum winds are. It's actually inward of that, closer. It's actually like the interface between the eye and the eyewall. So notice that you might not be able to see it here. There's like a red color right here at about, 0.8. So not quite where the maximum winds are, but inward of that. Spoiler alert, I think it may be associated with this kind of stuff that forms on the edge of the eyewall interface. But we'll see. And then TKE is still quite high all throughout the eyewall, but mostly, again, inward of the maximum winds, which is this kind of dashed black line. Okay, I promised you simulation results. I'm going to deliver simulation results. This is an idealized simulation I did of an ideal tropical cyclone. So it's a flat, ocean-only lower surface. We ran it with this grid spacing here, 32-meter horizontal grid spacing, 16-meter vertical grid spacing. I actually ran this simulation like 8 years ago on Yellowstone. So we're talking like 2 supercomputers ago. It took like, not that much, 500,000 core hours at the time, which now you can probably do that in like a couple 100,000 core hours in derecho or something. Maybe I should do that just for fun. But nevertheless, I had like this 50 terabytes of data from the simulation sitting around. We've been analyzing it. I've had a lot of collaborators from different federal labs and different universities. You can see a list here. This is a non-exclusive list. This simulation has probably been used in almost 10 papers by now. The method of simulation in the innermost part of the simulation is Large-Eddy simulation over an 80 kilometer by 80 kilometer domain. That's what you're actually looking at here. It's a relatively small storm. Not extreme. Storms this size happen, but they're kind of in the tail of the distribution in terms of towards the smaller end. I did that because I wanted to fit it into the machine, because if I have bigger storm, I need a bigger domain, and it would take a lot longer. So what does LES mean? It means you're basically running without a PBL, or Planetary Boundary Layer parameterization. That's the simplest way to think about it. And so the idea is to explicitly resolve the turbulence, as I'll show in a moment. There's lots of turbulence in the simulation. The detail, except very close to the surface, we're actually parameterizing a lot of the details near the surface. I don't have ocean waves. I parameterize the effects of the ocean waves. To make Peter happy, I used a 2-part model to make sure my wind profiles were. This is kind of a simple way to fix a known bias, if you will, in these models, which tend to overpredict the shear in low levels. Anyway, lots of details. You can look them up in a lot of these papers. Here's just another view of what I was just showing. This is a simulated radar reflectivity at 1 kilometer above surface. I'm using Hugh Morrison's double moment microphysics scheme. You see lots of turbulent details. One of the reasons I wanted to show that is because you see stuff like this in observations of hurricanes. This is a really nice study that Sim Aberson led in 2006 of Hurricane Isabel, showing, here's your eye wall where the highest radar reflectivities are, but they noticed a lot of turbulent, what I would call turbulent structures, a lot of details in this eye-wall interface. The eye's here, the eye wall's here where this high reflectivity are. Some people call these mesovortices. Some people actually think they should be called mesovortices. But key point here is the model produces something very similar, albeit at higher resolution. The radar has a certain resolution. I'm sure if you had a cloud radar scanning the inside of an eye of a hurricane, you'd probably see structure looking like this. This is what the vertical velocity looks like at, I believe it's 700 meters above the ocean surface. My colleague Chibozie Ogoijifor from Notre Dame, congratulations on passing your PhD prospectus exam the other day, 2 days ago. I'm on his committee. Anyway, I'm going to use his figure here. In fact, I think it's better to show it in quick time because I can slow it down. Here's what this animation looks like. This is output every second for a half hour, showing vertical velocity, the reds being upward, the blues being downward. It's really fun to watch this animation. You see all kinds of stuff. I'm going to grab, stop this and back it up a little bit. I like to pick out features and follow them in time. So you see these somewhat larger scale features on the eye-wall interface that kind of rotate around the eye for a while and have interesting structure. You see all kinds of linear organization outside of the eye wall. The eye wall itself is at this level is mainly upward, but even though it's primarily red, there's blues in there. And this is observed by aircraft as they fly through eye walls. It's very turbulent as you cross the eye, as you cross from outside of the eye to inside the eye in hurricanes. There's been some notable examples of some very turbulent and dangerously turbulent conditions in some of these reconnaissance flights. Yeah, so play this again a little bit faster. So thanks again, Chibozie, for the cool animation. Here's I think I have, just a few other pictures. I've shown these in previous talks. This is what the 10-meter wind speed looks like. This is instantaneous snapshot in the kind of the northeast quadrant of the eye wall. And you can see all kinds of interesting coherent structures there's a repeating pattern in here too, kind of a comma-shaped structure if you look real closely. Rich has talked about this. Yes, we'll get around to that paper and publish it eventually, Rich. I'm trying. Here's what the time average wind speed looks like. So this is instantaneous. This is if you average at every grid point for every model time step for a minute. So the peaks are 110 or more meters per second, but the average is around a little over 70. So this is a Category 5 storm. Remember this picture? This is Rob Rogers' TKE vertical cross sections. I tried to do the same thing with my model output using the same color scheme and in the same dimensions and everything. So 2 kilometers here is 2 kilometers here. Kind of a caveat, this simulation only had LES in the lowest 3 kilometers of the domain, and then it was non-LES up high. So that's why I'm showing only the bottom here. Here's how I define the perturbations. It's actually defined based on an azimuthal average. But the key point here is, hey, look at that. The TKE is a maximum inside of the location of maximum mean winds, which is R over RMW of 1. Remember, this is a normalized radius by the radius of maximum winds. TKE decreases with height in the eye wall. Quite similar qualitatively. There's no data in the eye in the observations because this is has an X-band radar and there's no scatterers in the eye, so there's no data. The LES actually has data in the eye, so it's If you believe the LES, it's quite calm in the eye. You have TKE values quite low. Actually, I haven't plotted the scale on here. The numbers are about an order of magnitude higher in my simulation than they are in Rob and company's analysis, and I'm not quite sure why that is. It may be because I have this small intense storm and they're averaging over a bunch of cases. Okay, this kind of ties a lot of the talk together. And in the last 5 minutes here, I'm going to talk about what came out of this analysis. This is what I've been working on for the last couple of months. I've told some people this is one of the hardest things I've ever had to code up, in part because these LES domains are big. Like I said, it's like 50 terabytes of data. It's annoying. What I did for this analysis is I actually restarted the simulation. I had my restart files from 8 years ago, pulled them off of campaign storage, dusted them off, squoze them into a newer version of the model, and actually write out these tendency terms actually captured from the model every 15 or 30 seconds or something like that. So calculate the advection term exactly as it was used in the model, pressure gradient, subgrid turbulence, buoyancy, and more. And then I also wrote out, like I said, the average of the velocities over the last 2 time steps. It's a multi-step analysis. First, I sweep through all this data, all 50 terabytes of it, and get time averages of everything, the U's, the V's, the advection tendencies, and everything. Do all that on the Cartesian grid with the Cartesian wind components. Then I sweep through it all a second time, getting the perturbations from the average and products of perturbations and anything I can think of wanting to calculate. And then I time average those, so you can come up with a U primed bar. That's what you're doing in this step here. And that's all done on Cartesian grid. And then step 3 ends up running much faster. So I write through that new 3D analysis, which is a much smaller file, sweep through that once, and interpolate onto a cylindrical grid for analysis purposes. And during that step, I project the Cartesian velocity components into the cylindrical components. The details of how to do this was actually laid out in the paper I was a co-author in with Dave Nolan a few years back. This is a study of a tornado. Now we're applying it to hurricanes. And finally, the quickest step of all, the one you're like, oh, thankfully, this code's been running on Casper for 8 hours, and now I can do the quick step. I can azimuthal average and present results that I can actually start looking at. And so that's what's actually going to be shown as the output from this final step on Radius Heights coordinates. And here's the most important figure from this analysis. This is the TKE itself, defined on the top here. This is resolved plus the subgrid component. E sub little s, that's the subgrid component. In fact, if you go down to the bottom here, here's a profile of TKE at its maximum value. Notice the maximum is 149 meters squared per second squared. Big number. So at 100 meters, 120 meters above the ocean surface, here's the black line, that's the total. The dashed is the resolved component, and the dotted is the subgrid component. So resolving the turbulence quite well from the perspective of this simple analysis. I just wanted to put that out there in case anyone asked. Location of maximum winds is where this white X is. The maximum value are radially inwards. So this is a radius. The center of the eye is over here somewhere. I'm only doing like the eyewall method. And then the eye and eyewall region, I should say. And the vectors here are the mean flow in this projection on this cross section. You can see the flow is inward, decelerates like mad where the high TK is, and then accelerates like mad vertically into the storm. The vectors are actually exaggerated a little bit in the vertical direction. The mean inflow is like 30 meters per second, and the mean updraft in the eyewall is of order like, I want to say like 5 meters per second. So yeah, if I did these vectors, and if this analysis is squashed down in a flat pancake like this, but I'm basically stretching everything so you can see it well. Some 3 sections I talked about in my abstract, and I'm going to cover briefly here is the inflowing boundary layer region. The corner flow, where you switch from inflow to eyewall upward, is technically called the corner flow. It's usually used primarily in the tornado community, but there's no reason it can't apply it in the hurricane community. And then there's this region above the eyewall. Okay, so that's the TKE. The title of this talk is the TKE budget. How did I get that? I went to Rich's office and I said, please, could you derive the TKE budget in cylindrical coordinates with azimuthal averaging. And Rich did this some years ago. I actually don't remember when, and he probably took like 2 hours to do it and like 6 sheets of paper. It would have taken me like 2 months and 60 sheets of paper. And, but anyway, Rich did it for me. Here's the math. yeah, I'm going to go through, show you each of these various terms. The main point in showing this is it's complicated, has a lot more terms than traditional boundary layer study, shall we say. A lot of terms associated with like radial gradients pop up that turn out to be important. And so instead of having like 3 or 4 things you could put on a line plot, now we have like, I actually plot 14 different terms you have to do in an RZ plane. It's really complicated. Here's all 14 terms. If you stop by my office in February or March, I had like this script running on my computer like constantly. I'm gonna go through all the details here. Yellows and oranges and reds are positive values. The blues and purples are negative values. The contour interval is shown up here, and the maximum and minimum are about 2.5 meters squared per second cubed. I said there were 14 terms. There's actually a 15th plot here, which is the residual. That's the sum of all these terms. And you can see it's not quite 0. It's got a couple contours on here. The maximum error is about plus 0.4 or minus 0.4. This is about 10% of the maximum in, so that's maybe within range, although Uncle Sam is like, damn it, George, I thought you said you had this worked out. I actually think I know where this remaining error comes from, and I was talking to Rich about that earlier, and I'm gonna rerun the simulations for the umpteenth time and see if I can figure that out. But anyway, earlier versions of this, if I plotted by residual plot, I had just contours everywhere. It was the budget did not even close to adding up. So when I started getting plots that looked like this, I was pretty darn excited. By the way, the gray shading on here is mean vertical velocity greater than 1 meters per second. That's where the eyewall is. Running out of time, so I'm going to step through this pretty quickly. These are the 6 mean gradient production terms that Rich identified. If you think there should be more, I don't know where you're going to get them from, but talk to Rich. He did the math. 2 of which are included in planetary boundary layer parameterization schemes and numerical models. And like we expect, they're actually quite large in a hurricane, particularly the one associated with the vertical gradient of the mean tangential wind. It's really high in the surface layer. By the way, Joe Sion just got a funding this week to fly a bunch of drones again. So I'm hoping to convince him to fly down here, way, way close to the surface. The other one that's vertical gradient of the mean radial wind, we expected that to be important. This term here, it's like the radial gradient of the tangential velocities. This is like winds are weak in the eye and they're strong in the eyewall. And a lot of people thought that this term would be large, but it's not. It's actually, it's kind of matters like right in the bottom corner of the corner flow, but probably negligible. The term that was surprisingly large is one that's associated with the variance of the U component, the radial component. This is into and out away from the storm. So fluctuations toward and away from the storm multiplied by the radial gradient of the mean radial velocity. You catch that? I know what that means because I've been thinking about this term in my dreams for weeks now. This is definitely not included in any PBL parameterizations, but the model simulation suggests like underneath the eye, that may be the main source for turbulence in hurricanes, and we don't have it in our numerical models right now, our weather prediction models. 2 more minutes and I'll wrap up here. The transport terms that arise, the other terms that arise out of the advection term. Here's TKE, again, I'm using uppercase E here. The mean, the advection of TKE by the mean flow turns out to be kind of important. This is the one Xiaomin and I identified in our paper using the MYNN is important, and it's kind of important. But a caveat is, if you go back to this slide here, this mystery term again, it's quite high throughout the eyewall, and it's not in our model. So we identified this as important, but it's the only term we had in our mesoscale model or cloud model type simulations. Turbulent transport terms, these are pretty important and included in PBL schemes. Basically this dashed line means this is sometimes included in PBL schemes. It's often neglected just for cost. I mean, who wants to calculate an extra advection calculation in your model? So a lot of operational models just throw that out. In MYNN, you can turn it on in WRF pretty easily, same as in CM1. The best of the rest, dissipation, pressure, and buoyancy. Dissipation is definitely included in PBL parameterizations, but if you're trying to use an LES to help you tune your model, I think you need to tease out the part that comes from the dissipative advection scheme, which is the one with the uppercase D here. This is what comes from your turbulence parameterization model. It's definitely playing a big role in the surface layer, but as you move up into the eyewall, these two terms are comparable now. In fact, you might even say your fifth order numerics are creating more dissipation than your parameterized turbulence. Buoyancy is negligible according to simulations, which a lot of people are going to give me grief about, but we'll see how this goes when I present this at a conference. It's actually weakly positive near the surface and weakly negative in the eyewall. And then the pressure scheme is kind of included in PBL schemes. It's usually just wrapped up with this turbulent transport team and just parameterized in a crude way, and it's hard to account for, actually. And then I had grand plans to talk about all these regions and what's going on here, but I pretty much talked about a lot of this. And one thing I'll just point out, again, this U prime squared to U bar dr term is surprisingly large. And at least in these simulations, the advection of TKE by the mean flow is surprisingly large, but that may be because I have this relatively small and intense storm. Anything else to point out from here? Some people think buoyancy should be positive in the eyewall. It's actually negative in my simulations. This doesn't surprise me though, because strong hurricanes in particular it's argued, and I think it can be shown, are moist slantwise neutral, and that by definition, it's unstable in a slantwise direction or neutral in a slantwise direction. In the vertical direction, it's stable. Kerry Emanuel built a whole award-winning theory out of this years ago. So I wouldn't expect buoyancy in the traditional sense to be positive in the eyewall. If you maybe do this analysis on angular momentum surfaces, maybe you can see some positive buoyancy, but we'll see. Here's my summary slide. I'm going to skip through these terms, in the future, I'd like to examine kind of larger and also weaker storms, just to make sure some of these terms I see aren't just a factor of this kind of extreme end of the storms. This radial advection of TKE and this funny term, I don't know what to call it, I'll have to come up with the term. I'll call it the Rotuno term for now. May not be as large in these sort of larger storms with larger eyewalls, and that's what I want to do in the future. All right, I'll stop talking now since it's been almost an hour. Thanks for your time.
Okay, we're open for questions, comments. In the back, Chris.
Yeah, Chris has a question, but he's way in the back. Can you throw the microphone?
So the Rotuno term, the mystery term, how do you think this might relate to the structures you were showing on the inside of the eyewall earlier in the talk? And is this a result of those, connected with those?
Yeah.
The same thing? Do you have a sense for that?
Not really, not a deep sense. It's something we're actively thinking about. I should point out, as you flow in towards the center of the storm, so 90% of the storm is covered by this rotating, inflowing air. And the mean case in a hurricane is DUDR is negative. So this term, no, it's DUDR is positive. So this is actually a weak negative term. It's kind of a weakly negative term. And then when you get in this corner flow region, then that U immediately switches sign, and it does so in a big way. And it has to switch sign because the air is going up and by continuity. And then you have all this turbulent flow, which you shove into that environment. And you have all these fluctuations. And so fluctuations that are going in towards the storm in this gradient where U is slowing down. So you're tossing patches of air in this environment where you have this turbulent flow. And it's like a dynamic wall. It's this big pressure, which is slowing, big pressure perturbations is slowing the air down, but you have all these perturbations in it. So that's the small scale dynamics. Now, why that is a positive and why that amplifies flow is something I guess Rich and I are kind of working on. I suspect that it's essentially responsible for those kind of larger scale structures you see. To prove that, I think you'd have to run maybe some even more idealized simulations, or even run some of these like, what is Dave Nolan's kind of code? It's like a linear perturbation growth analysis. I bet he'd show that perturbations grow in that kind of environment. But why is the big question. And what sets that scale? It may be that the corner flow region is a couple kilometers wide, so maybe that's why you get these big eddies. It's real tempting to think that, but we don't have the detailed analysis yet to prove it. They're passing around the microphone in here in case you can't see.
I just want to comment before Peter comments that Peter and Jim Jim McWilliams have seen the same kind of term in their frontal simulations.
We actually have two.
And you got two of them.
Yeah, there's a U prime, V prime. In frontogenesis in the water, that's really, really strong. We find a rich term, U squared times basically that same gradient, but it's also, we have U prime, V prime times that same gradient.
Because you have two-dimensional in like a Cartesian sense, yeah.
The other thing that happens is the turbulent transport is actually the big balance in that region, not dissipation. That was the thing that really, really surprised us.
That would be like these two terms here, I guess. So yeah, this one's kind of big. Yeah, I'm sure there's plenty of analogs in the literature out there in other cases, but yeah. So Peter's talking about they have like convergent flow in the ocean, and then you get this frontogenesis, but at some point, the gradient is so big it just bursts out in turbulence, which acts to halt that frontogenesis, and you get all kinds of interesting turbulence in there, which is what he's studying the dynamics of with Jim McWilliams. Holy cow, there's a lot of questions online. So.
Okay, I will just make one more comment to respond to Peter's. We have U prime, V prime, but it's not playing a big role here because it's multiplying the gradient of rotation rate. Okay, on to the, let me
Okay.
have to get closer to read these. Okay, related to your comment on the location of TKE max on radar observation slide, one might anticipate maximum TKE to be where radial shear turbulence production rate is maximum, which is not the same place as maximum wind. Is that the case? Also in your simulation slide, is
Right.
Jim Brazier.
So max TK would be the radial shear turbulence production rate. Not sure exactly what you mean, Jim, by the radial shear turbulence term, because maybe that's the one we've been sort of blaming Rich on, this one here. But yeah, I actually have a sort of analysis I haven't shown here that, yeah, the maximum tendency is inward of the location of maximum winds. And I think that's what you're asking also in your simulation slide. So I think is that the case? I think the answer is yes. Yeah. Peter's nodding his case, yes. But,
Okay, let's go to the next question. Next question.
yeah, thanks, Jim. It was good to see you a week or so ago.
Hey, George. We should give Nathan Dahl the credit for the Cartesian to cylindrical conversions of eddy terms. He did all that. Back to AB slides. Why do you have to expand out the differences? Why not just compute the time differences of AB like on the left side of the slide?
Okay, so first, yeah, good point. I didn't know that Nathan did a lot of the analysis. This ended up in the paper, I think, Dave, with you as the first author, so I actually didn't know who did that. So thanks, Nathan, for doing a lot of that math.
That the time on your thing was years and years before that, though, on your...
Yeah, I'm sure somebody's done it in literature before then, but yeah. The AB slides, why not just compute the time difference? You can. The issue here is, that'd be for the left-hand side of these terms. What I want to do is the right-hand side. I want to know what contributes to the total tendency. So in other words, when I go back to, darn it, if I don't find it in a moment, then I'm going to give up. There it is. So sure, Dave, I think you're asking why can't you just do that calculation of A times B term, and I think that's what this is here. But I want all the contributions to that, which you then need. You have different U's and A's, And I'm not sure if that answers your question, though, or not.
Just so I had a similar question. I think I understand his question. I think it's a couple slides forward. Sorry. That slide. Sorry, it's just, I think this is what that question is referring to, but I had a somewhat similar or like related question here.
Yeah.
So I think he was asking, why not just use that like bottom left formula? I don't know if that's just a limitation of what outputs you have or something.
But this is the left-hand side of this equation. I mean, the right-hand side has, it doesn't have A times B. It has, like the turbulence terms are d tau dz.
Yeah, so you don't have like a decomposition.
And the question is, what do you multiply that by d tau dz by? And so the obvious thing is, look, I'll just multiply it by u that I have in my output. But this analysis shows that to be consistent, you have to multiply by the u averaged over the time step.
Yeah.
Now, yeah, if I only wanted the total, so switching past Uncle Sam a couple times. If I wanted the left-hand side of this equation, that's exactly what I could do. If I want all the terms that contribute to that, I have to consider these extra terms. I think that's what I'm saying.
Yeah, so just one other thing that was question I had about the AB slide again, which is you have the error listed, and it looks to me like that's like a first order error, but then what you have on the left is only a first order accurate formula anyway. So is this is not like an order of accuracy change, it's more like consistency with the rest of your numerics? Is that why this helps to close the budget? Or just like the size of first order error?
This kind of gives you the magnitude there. This does bring up an interesting point. You know, if you change the time step, reduce the time step, you're going to reduce the error because it's a first order, but it would change that in excruciatingly slow. You have to have a really small time step to kind of start getting budgets that are accurate, I think is, thanks for pointing out the order of the error. But yeah, what I was attempting to do here was kind of come up with an order of magnitude. So you can actually calculate these terms on the right-hand side by the way I was doing it before in a simple way, but then actually add on this term and it should actually compensate. This might actually be easier to do than the way I did it. Because you don't need U average over the two time steps. You actually have everything you need in a traditional model output. You have all the tendency terms and the U, or in this case, U at the two times. And then instead of, you can account for the error with two terms you already have, I guess is what where I'm going with this.
So I think I'm going to have to cut it off here since we're significantly over time. You could, Jimmy, you could ask George your questions when you come in sometime. Yeah. So thanks again, George. Great setup.